Okay, as we did the last time, we'll start with the answers to the questions. And these are the questions that were at the end of the lecture for Chapter 35. This seems to be the one weak spot for some of you, both in your tests and when you are answering your problems. So first of all, if the index of refraction of a given material is 1.5, what is the speed of light in the material relative to the speed of light in a vacuum? And the answer, of course, is C, right? The speed of light does not change there. Blue light travels from air into glass that has an index of refraction of 1.54. How does the wavelength of light in air compare with the wavelength of light in the glass? And that is B, the wavelength of light becomes shorter in the glass, right? Because it's a higher index of refraction, wavelength becomes shorter. A single beam is split into two equal beams, denoted A and B. Beam A travels through a medium with a higher index of refraction than the medium B travels through. When both beams exit their media back into air, how do their wavelengths compare? And the answer is C. Both beams have the same wavelength. They're both back into air, and so that's going to change them. Whatever it changed that they had before is going to go back to what it was prior to that. So the answer to that is C. 4. Which of the following must be satisfied if interference is to occur for light passing through a single slit? And it's here, reducing the slit size only increases the number of maxima, but the location of the initial maxima are not changed, okay? So that's the slit size increases the number, but not the location. Number 6. What? Did I miss one? I'm sorry. Where? It looks like I did miss one here. Okay, which of the following must be satisfied if interference is to occur for the light passing through a single slit? And this is the answer, D. The width of the slit must be comparable to the wavelength of the light. Okay. This next one right here, this actually is B. The distance between the maxima increases as the widths are reduced. Okay. When the size of the slit is reduced. Maybe I had those in the right sequence, but somehow it looks like it has skipped one. But the answer for 5 definitely is B. The distance between the maxima increases the width as the widths are reduced. Then we get to 6, and again, what happens to the width of the maxima for double slit interference when the size of the slit is reduced? And again, it is the width of the maxima increase as the slit size is reduced. So again, the answer is B. In a shallow pool of water, there are two needle-like dippers that move up and down at constant frequency. The water waves move outward from each source as shown. The wave crests represented by solid lines have an amplitude of 0.4 centimeters. Okay. What is the displacement of water relative to the undisturbed water level at the point P? Okay. And so that is going to be minus 0.8 centimeters at that particular point. That's a minimum, and the two of them are overlapping at that particular point. Okay, so it's going to be E. Whoops, boy, we just skipped right ahead there. This is A. Sorry. Let's C right here is this one right here at this particular point is minus 0.8. This one right here, this is a maximum for both of them, and this is A plus 8. I'm gonna have to watch this. This is seems to be skipping on me a few times. Okay, number 9. In Young's double slit experiment, green light is incident on the two slits. The resulting interference pattern is observed at a screen. Which of the following changes would cause the fringes to be spaced further apart? And the answer is D. to change the wavelength. Use orange light instead of green light. Okay. 10. The beam of monochromatic light with a wavelength of 660 nanometers is directed at a double slit. Consider the 5 fringes, A, B, C, D, and E, in the drawing, including the central maximum, which is B. Which one of the fringes is 330 nanometers closer to one slit than it is to the other slit? And that would be A. Okay, here the beam is at 660 nanometers is detected by the double slit. 5 fringes. Central is at B. Okay, which one of these fringes is produced when the path difference is 1,320, which is twice that? And the answer would be D, way out here. Okay, that's the second one out there. You are sitting in a closed room with no windows. The only light in the room originates from 2 identical bare incandescent light bulbs. One is located on the wall to your left, the other is located on the wall to your right. Bored, you look up at the ceiling and realize there is no interference pattern. Why is there no interference pattern? And the answer is that 2 light sources are not coherent. Okay? They have to be coherent in phase for them to have an interference pattern. Okay, here we have 2 wave pulses are sent down a stretched out rope. Pulse A is traveling towards the right, amplitude of +2 millimeters. Pulse B is traveling towards pulse A from the right to the left with an amplitude of -4 millimeters. When the 2 pulses meet and completely overlap, what will be the maximum displacement of the rope relative to the undisturbed position? Okay, and the answer is going to be simply the sum of those, -2 millimeters, right? Which of the following choices does not affect interference of light when the thickness of a thin film is much less than the wavelength of light? And that is A, the path length difference. The path length difference does not change when that occurs. For 15, a special system is set up in a lab that lets the user select any wavelength between 400 and 700 nanometers with constant intensity. This light is directed at a thin film, refractive index 1.53, thickness 350 nanometers, that is surrounded by air. As one scans through the possible wavelengths, which wavelength of light reflected from the glass film will appear to be the brightest, if any? And the answer will be 420 nanometers. 420 nanometers. Okay? Here, blue light, lambda is 512 nanometers, is illuminating a thin film of plastic. Refractive index is 1.60. On top of a glass sheet, refractive index 1.45. Which of the following statements best describes the light that an observer sees coming from the thin film if it has a uniform thickness of 0.2 microns? And the answer is D. We will see the film as uniformly dark due to destructive interference. You can also do the same sort of a thing with by creating soap bubbles, and those are when they could drain to a very specific level, they're called black films because they have completely destructive interference as well. But the answer for this one is D. And then finally, 17. Blue light, lambda 512, is illuminating a thin film of plastic. Here's 1.45, on top of glass 1.53. Which of the following statements best describes the light that an observer sees coming from the thin film if it has a uniform thickness of 0.265? And here, it's constructive interference, so this is going to be uniformly bright. The answer here is going to be C. Okay? So all of those rely very much upon the equations that we had for those of what the effect of the thickness is and the effect of the index of refraction for the different materials. And that is it for this particular section. We'll go on now and start with the lecture portion. You'll see that I also have posted the problem solutions for the ones for the end of chapter 35 as well. All of you did quite well on those. It was these questions right here that appeared to give you a little bit of fits.